Everyone. Today I'm going to be presenting on homomorphic encryption. I'll be going over what homomorphic encryption is, the history of homomorphic encryption, the operational mechanisms, the fundamental principles, and some of the limitations and challenges of homomorphic encryption. So what is homomorphic encryption? Homomorphic encryption is a form of encryption that allows for computations to be carried out on ciphertext, generating a result that is still encrypted, and when the result is decrypted, it would match the results of the same operation if it was done on a plain text. This type of encryption is significant because it enables data to be processed without granting access to the unencrypted data, providing a powerful tool for preserving privacy in cloud computing and data analysis environments, allowing mathematical operations on data like addition, subtraction, multiplication, and division. The term homomorphic comes from algebra and refers to the preservation of structure. In the context of encryption, it means that operations performed on encrypted data will still make sense when decrypted. The first plausible construct for completely homomorphic encryption was described by Craig Gentry using lattice-based cryptography, which is a cryptographic system that derives its security from the complexity of lattice problems that involve points in multidimensional space. The construction that Craig Gentry described allow for both addition and multiplication operations on encrypted text. Each ciphertext contains an amount of noise due to the cryptographic operations. When ciphertexts are added or multiplied together, this noise grows until the noise eventually renders the ciphertext undecipherable. These operations Craig Gentry conducted on a simple bit operation would take up to around 30 minutes. The second generation of fully homomorphic encryption systems are derived from techniques developed from 2011 to 2012 by a couple of people that I can't pronounce the names of, and Craig Gentry and others. The innovations made led to the development of much more efficient, somewhat and completely homomorphic crypto systems. All the second generation crypto systems still follow the basic blueprint of Gentry's original construction. They first conduct a somewhat homomorphic crypto system and then convert it to a fully homomorphic crypto system using bootstrapping. These crypto systems allow much slower noise growth during the homomorphic calculations than the original construct developed by Craig Gentry. They're also efficient enough for many of the applications today, even without calling the bootstrapping process and circuit. The third generation of fully homomorphic encryption systems are based on a technique that avoid an expensive relinearization step in homomorphic multiplications. These third generation crypto systems exhibit an even slower noise growth rate for certain circuit types, thus giving a better efficiency and stronger security. More efficient bootstrapping techniques were developed based on these observations, which resulted in a significantly simplified bootstrapping process, reducing its time to a fraction of a second. Fourth generation expands even further on the previous generation, significantly reducing noise and reducing the number of bootstrapping circuits through innovations in machine learning. These fourth generation schemes use encoded estimated values instead of exact values, which, due to working with rounded values, there are vulnerabilities that arise. So most of the fourth generation is more focusing on being able to improve and scale homomorphic encryption. The basis of homomorphic encryption, as stated previously, is based on incredibly hard mathematical problems such as lattice-based cryptography or integer factorization. Just like other cryptography systems we've learned, homomorphic encryption schemes are set up by generating keys and encrypting the plain text into ciphertext. But homomorphic encryption performs arithmetic operations on the ciphertext. The complexity of the operations on homomorphic encryption makes them computationally more intensive and slower than their unencrypted counterparts. The main goal of these encryption systems is to make sure that you're able to effectively transform data without having to decrypt it. This means that there's a significantly lower chance of lapse in security, as the sensitive data that's encrypted remains confidential even during its processing. This makes it a crucial area of studying cryptography in our data-driven world today. One of the homomorphic encryption schemes is the one that we've been learning, RSA encryption, which uses modular arithmetic in its encryption and decryption process. Because of these encryption systems using modular arithmetic, they're able to conduct nonlinear operations like multiplication and exponentiation on the encrypted data. This ability is essential for homomorphic encryption, and getting to much more secure and computationally difficult homomorphic encryption techniques, such as those based on learning with error problems or ring learning with error problems, use modular arithmetic in polynomial rings, typically involving operations where the coefficients of polynomials are reduced modulo some integer. RSA is a partial homomorphic encryption, which means that it allows for one type of operation, either addition or multiplication, to be performed on ciphertext an unlimited number of times. For RSA encryption, that operation is generally multiplication, meaning the product of two ciphertexts will decrypt to the product of their corresponding plaintext. Somewhat homomorphic encryption extends on the capabilities of partial homomorphic encryption by supporting both addition and multiplication, but only a limited number of times before that noise within the ciphertext grows too large to manage, which will lead to decryption errors. This allows somewhat homomorphic encryption to be more flexible because it supports more complex computations, but is still limited in the depth of computations it can handle. Fully homomorphic encryption is the most versatile among the three, allowing both addition and multiplication operations to be carried out an unlimited number of times without degradation in security, meaning arbitrary computations can be performed on encrypted data. One of the most substantial challenges in implementing homomorphic encryption is its high computational overhead. The operations are considerably slower compared to the operations done on plain text or those encrypted with traditional methods. This requires significant computational resources to complete, impacting the performance, but also increasing the time needed to process data, making it impractical for real-time applications or environments where computational resources are limited. The implementation of homomorphic encryption is also inherently complex, arising from the need for specialized knowledge to correctly implement and manage. Additionally, the overhead related to computation and management increase the cost of infrastructure as more powerful servers are needed to handle the computational load. This represents a significant barrier to adoption, especially for smaller organizations or applications where cost efficiency is crucial. While homomorphic encryption provides strong theoretical guarantees on data privacy, it introduces unique security concerns. For instance, there's an increased attack surface from the need of a more complex code base and the unusual nature of the computations. There are limitations on homomorphic encryption, and that's due to them only typically supporting a limited set of operations, with most schemes being partially homomorphic, meaning they support either addition or multiplication, but not both. Fully homomorphic encryption, which supports unlimited operations on ciphertext, is still not broadly practical due to its computational needs. Homomorphic encryption is used in the medical field to securely process sensitive health data while maintaining privacy and compliance with regulations like HIPAA. For example, researchers or healthcare providers might need to aggregate and analyze patient data to identify trends or improve treatment protocols without accessing individual patient records, which homomorphic encryption would allow. For voting systems, homomorphic encryption offers a method to ensure that votes are counted accurately while maintaining voter anonymity and vote confidentiality. In such a system, each vote is encrypted before it's cast, and the encrypted votes can then be combined and processed to compute the total for each candidate. In banking, homomorphic encryption can be used to secure financial transactions and protect sensitive client data during analysis. For instance, a bank might use homomorphic encryption to perform risk assessments and analyze client portfolios without accessing the actual data in clear form. This also allows them to comply with financial privacy laws and regulations by ensuring that customer data remains encrypted even during processing. This has been my presentation on homomorphic encryption. If you have any questions, feel free to reach out. There's also a plethora of documentation and research on homomorphic encryption that you can access online. Thank you.